So when you think about the ideal hamburger, what do you think about? You probably picture the perfect hamburger, all the conditions are excellent, but deep in your heart, you know that it could never be. Chemists think about gases the same way, and ideal gases are ones that are perfect. They're ones that behave all of the gas laws under all conditions. They don't condense into a liquid when they're cooled. When you graph them on a volume versus temperature or pressure versus temperature, you get a straight, perfect line. But it's not true. It never actually happens. Those are just ideal situations. And most of the time they are true. They follow those patterns, but it doesn't actually happen. What we use when we talk about ideal gases and the ideal gas law that I'm about to show you is we are making it easier to quantify. So by imagining gases behave ideally, by pretending that they obey all the laws perfectly, we can simplify our equations and make it a lot easier. Otherwise, you have to do a lot of tricky stuff in there, and just be thankful that we use the ideal gas law. So here it is, the ideal gas law. So this equation, it's not like the other gas laws where things are changing. Rather, this is used to analyze a single system of gas. So we've got a certain pressure, a certain volume, a certain temperature, and a certain number of moles. It's locked into those conditions, and we're just analyzing it. So a way you would recognize an ideal gas law question is when there's nothing changing. We're just looking at certain conditions. The equation, as it spells out here, is commonly known as PERV-NERT. PV equals nRT. PERV-NERT. P is pressure, and one of the really important things for the ideal gas law for PERV-NERT is that all of the units have to be certain things. So pressure must be in atmospheres. Volume must be in liters. N, that is moles, and so it must be in moles, can't be in grams or anything else. And T, which is temperature, just like the other gas laws, has to be in Kelvin. So step number one when you're doing a PERV-NERT equation is to always convert your units. Before you do anything else, before you plug any numbers in, make sure you convert. Get it done right away, that way you don't forget to later on down the road. A lot of the times things are going to be measured in milliliters, or they're going to be measured in kilopascals or Celsius, and you have to convert to moles, liters, atmospheres, and Kelvin. Now you're probably wondering, Mr. Jones, what does that R stand for? Does it stand for rutabaga? It does not. It stands for ratio. R is a constant. It's the gas constant. That means this number is always the same. Okay, no matter what ideal gas law equation, no matter what the situation is, R will always be the exact same number. And that number is 0.0821. So anytime you're using a PERV-NERT equation, you can plug 0.0821 in for R. It's always that. The units of R are liters, atmospheres, moles, Kelvin. Now, once again, those are units. That is not a separate equation all of its own. Just like volume is in liters and N is in moles, R is liters, atmospheres, moles, Kelvin. It's just a lot of different things on there, like the speed of your car is miles per hour. This is liters, atmospheres per mole, Kelvin. So it's just another unit. So with PERV-NERT equations, once again, everything will be under certain conditions. Nothing is changing. That's how you recognize it. You're always going to be given 3 because there's 4 variables that can change. Pressure, volume, number of moles, and temperature. R can't change. So 4 things that can change. You're going to be given 3 conditions and asked to solve for the last one. So you might be given pressure, volume, and the number of moles and asked to find the temperature. Or the temperature, number of moles, and volume and asked to find the pressure. So step number 2 then, once you know what you're solving for, is to rearrange the equation before you plug any numbers in. This is a piece of advice that I would strongly encourage you to follow. So take this equation and rearrange it to solve for what you want to find before you plug numbers in. It's going to make it a lot simpler rather than having a bunch of numbers you have to move around and solve ahead of time. It's going to solve you a lot of algebra headaches if you do that step, and we'll see some examples of that. And then the last step is then to finally plug and chug. So once you've converted your units, you've rearranged the equation to solve for what you want to solve for, then you plug everything in and solve for it. So we said that gases don't behave ideally all the time, but there is a certain set of conditions in which they behave the most ideally. And those conditions are STP. STP stands for Stone Temple Pilots. No, I'm just kidding. It stands for Standard Temperature and Pressure. So STP is a set of conditions that scientists kind of agree, hey, here's where gases behave the best. Anytime that we do research on gases, let's try and put them at standard temperature and pressure, so at STP. You'll see several questions or several labs where it says convert the units to STP or solve for this gas when it is at STP. And so you need to know then what STP means. So standard temperature and pressure, that means there is a temperature and a pressure for gases at STP. The temperature for gas at STP is 0 degrees Celsius, which is also 273 Kelvin. And the pressure at STP is 1 atmosphere. Okay, so remember that. Anytime that you see the conditions STP, it's not going to say STP, temperature is 0 degrees Celsius, pressure is 1 atmosphere. It's just going to say STP. And you need to know that that is 0 degrees Celsius, 1 atmosphere. Alright, here's our first practice problem with PervNerd. So what is the volume of 1 mole of carbon dioxide at STP? Now looking at this problem, notice how there is nothing changing. The volume isn't changing, the temperature isn't changing. It says certain set of conditions, so that tells us that we're talking about the ideal gas law. Okay, if we look at what we have here, we have moles. So we have the N, we have the standard temperature and pressure, which means that we have temperature and pressure. We always know what R is. R is always 0.0821. And we're asked to find the volume. That means we are solving for V. So step number 1 is to convert things. Well, we've already got everything that we need. So STP, that means the pressure is 1 atmosphere. Number of moles is 1 mole, temperature is 273 Kelvin, and R is 0.0821. We don't need to convert anything in this case. Step number 2 is to rearrange the equation. So here's what I mean by that. Let's not take these numbers right here and plug them in and then try and solve for V. Instead, let's rearrange this equation so it is solving for V. That means since we want to get V by itself, if we divide both sides by P, that'll cancel it out on that side, and we bring it over to there. That means our equation, in order to figure out the volume, is going to be nRT divided by P. By doing that right there, that means we're putting all of the numbers on one side and our variable on the other side. It's going to make solving a lot simpler. Now we can take the numbers and plug and chug. Alright, so there's all of our numbers plugged into their proper place. So 1 mole times 0.0821 liters atmospheres moles Kelvin times 273 Kelvin divided by 1 atmosphere. And that'll tell us the number of moles in the volume of a gas sample that's 1 moles at STP. So if we solve that, we get 22.4 liters. Okay. It doesn't matter that it's carbon dioxide that we're talking about. Any gas, actually, at STP is going to occupy a space. If you have 1 mole of any gas at STP, it will occupy a space of 22.4 liters. So that means if we take a 1 mole sample, boil it until it's a gas, and bring it to STP, the space it will occupy is 22.4 liters. So that's like 11 2-liter pop bottles of soda full of gas. And that would be 1 mole. Alright, and 2 more practice problems. So hey, if you're feeling comfortable with it, go ahead and pause it, try both of these, then resume the video to check your answer. Otherwise, follow along for one or both of them. Alright, so this first one is asking us how many moles, that means we're going to be solving for N, of hydrogen gas is in a 3.1 liter sample of hydrogen measured at 300 kilopascals and 20 degrees Celsius. Step number 1, let's convert. 300 kilopascals ain't gonna cut it. 20 degrees Celsius, So let's convert this one over to atmospheres. Let's remember that 300 kilopascals and 1 atmosphere is 101.3 kilopascals. And so that means that we have 2.96 atmospheres, and that's going to be our pressure. Temperature, same thing. Let's get rid of that. And 273 plus 20 is 293 Kelvin. Okay. Now that we have the 2 proper pieces of information, we can go ahead and figure out what our equation is going to be. So here's PervNert, but we want to solve for N. So if we rearrange this by dividing both sides by RT, that means that the number of moles is equal to the pressure times the volume divided by R times T. Now we can plug and chug. Alright, so there's all the numbers put in the proper place. 2.96 atmospheres times 3.1 liters divided by 0.0821 liters atmospheres moles Kelvin times 293 Kelvin. And when we go ahead and solve that, we come up with 0.38. And since it's N, and N is moles, and the units of that have to be mole. So if we had 3.1 liter sample of hydrogen gas, pressure is 2.96 atmospheres, temperature is 293 Kelvin, that means inside of that sample there would be 0.38 moles worth of gas. Alright, then the second question, how many grams of oxygen are in a 315 milliliter container that has a pressure of 12 atmospheres at 25 degrees Celsius? Now, in this case, they are asking us for grams. There is nothing in PervNert about grams, but there is moles. And there's not possibly a way to convert moles into grams or grams into moles, is there? Yes, there is, and we know how to do that. So if we find the number of moles, we can use the molar mass to convert it into grams, and we can figure out what the mass of oxygen would be inside that sample. First off, though, let's convert units. So the 315 milliliters, no way, Jose, that has to be 0.315 liters. Pressure of 12 atmospheres, that one's okay. 25 degrees Celsius, though, we need to convert that into Kelvin, and it's going to be 298 Kelvin. Now, since we're solving for moles, we can just use that same equation that we used last time, N equals PV divided by RT, and we can plug those numbers into their proper place. So 12 atmospheres, 0.315 liters, 0.0821 liters atmospheres moles Kelvin, and 298 Kelvin tells us that we have 0.16 moles worth of oxygen gas. So if we have 0.16 moles of oxygen, we know that one mole of oxygen weighs 32 grams. So moles cancels out moles, and if we multiply 0.16 by 32, we would find out that the sample weighs 5.1 grams. So we would have 5.12 grams of oxygen in that sample. So there you go. There's the ideal gas law equation, PervNert in a nutshell. It's all about analyzing a certain system of gas. This will be used in laboratories a lot because it'll be a certain temperature that you're collecting at. The room will be a certain pressure, and we can calculate how many moles or the volume based upon this equation right here. So we are going to have several opportunities in class to use this during a lab.